last part we have seen amphoteric nature of water, which means water act as acid as well as base. Now here I am going to start new point. The point is Ostwald dilution law in case of weak acid. Now first of all, what is Ostwald dilution law? Ostwald dilution law means it is the relation between a dissociation constant K and degree of dissociation alpha. So Ostwald dilution law, which means it is the relation between K and alpha, which means K means dissociation constant and alpha we know that degree of dissociation. So Ostwald dilution law is defined as it is the relation between K and alpha, or we can say that Ostwald dilution law is defined as the relation between dissociation constant K and degree of dissociation of weak electrolyte. Now we are taking Ostwald dilution law in case of weak acid, and weak acid such as HA. We can represent weak acid like this, HA. And we know that when weak acid dissolve in aqueous medium, it dissociate into ions. So when the weak acid such as HA, when dissolve into the water aqueous medium, it gives ions H plus plus A minus. So this is positive ion we got, and this is negative ion. So as we know that when weak acid dissolve in water, it gives us ions. One is positive ion and other is a negative ion. So HA, weak acid, when dissolved into the aqueous medium, it gives positive ion H plus and negative ion A minus. Now for this weak acid, there will be a acid dissociation constant Ka, where Ka is called acid dissociation constant. We know that K means dissociation constant and subscript A for acid. So in case of acid dissociation constant, we can represent like this, Ka. And in case of base dissociation constant, we can represent like Kb. So here, because the weak acid is there, in case of Ostwald dilution law, the A for acid and K for dissociation constant. So combinedly K is called acid dissociation constant. So acid dissociation constant for this reaction, it will be concentration of H plus into concentration of A minus divided by concentration of Ha. Now always remember that whenever there is a acid dissociation constant or base dissociation constant, the product side means ion side are above the line and reactant side is below the line, which means the ions, whether it is positive negative ions, are above the line, means numerator part of division, and whereas the reactant side below the line means denominator part of the division. So Ka, acid dissociation constant for this one, is equal to concentration of H plus into concentration of A minus, product side on the upper side, on the top of the side above the line, divided by concentration of Ha. We can represent concentration by using square bracket. So this is the acid dissociation constant for this one. K is equal to concentration of H plus into concentration of A minus divided by concentration of Ha, weak acid. Now coming to this, again I will write the weak acid dissociation Ha, same reaction Ha, reversible one, because it is a weak acid, so that is why we can use a double-headed arrow, means reversible between reactant and product. So Ha, coming to this, Ha reversible one gives H plus plus A minus. Now here we have total three conditions. At time t is equal to 0, means before the start of the reaction, then time when the reaction reaches at equilibrium stage, and last one the concentration at equilibrium stage. So first one, when the time is t is equal to 0, means before the start of the reaction. Suppose before the start of the reaction, means we have t is equal to 0, time t is equal to 0. Before the start of the reaction, we have only one molecule of weak acid, Ha. So at time t is equal to 0, before the start of the reaction, we are supposed to have only one molecule of Ha. So because the reaction is not started yet, the amount of H plus and A minus, that will be 0, because the reaction is not started yet. We have number of moles in case of HA weak acid is only 1, supposed to be 1. Then when reaction reaches at equilibrium stage, out of 1 alpha moles will be dissociated. So out of 1 alpha mole will be dissociated. So at equilibrium stage, when reaction reaches at equilibrium stage, out of 1 only alpha means partial dissociation. We know that in case of weak acid, the dissociation is only in small extent, means partially dissociated. So out of 1, when reaction reaches at equilibrium stage, out of 1 only alpha moles dissociated. So out of 1 only alpha moles dissociated. So here how much moles remaining? 1 minus alpha. So HA, number of moles remaining after dissociation, that will be 1 minus alpha bracket. So this is the condition when reaction reaches at equilibrium stage. So this is the condition before the start of the reaction. We supposed to moles 1 0 0 at equilibrium stage, out of 1 alpha moles dissociated, so remaining moles 1 minus alpha. Suppose we have 100 moles of HA instead of 1, and 100 out of 100 only 5 moles dissociated. Suppose we have 100 moles of HA instead of 1, and out of 100, because the weak acid is, only 5 moles are dissociated, which means how many moles remaining in case of HA? 100 minus 5. So 100 minus 5, that is the moles remaining. So I am considering here 100 means 1 and 5 means alpha. So out of 1 alpha dissociated, to remaining moles 1 minus alpha. Likewise 100 minus 5. So this is the equilibrium stage, the amount at equilibrium stage, amount of HA, 1 minus alpha, H plus alpha and A minus alpha. Now third condition, the concentration at equilibrium stage. Now we know that concentration means number of moles divided by the volume. So we can divide each term by the volume. So this is the concentration, third term. So we can divide each term by volume, because we know that concentration means number of moles divided by the volume. So we can divide each term by volume. So 1 minus alpha by V, here also alpha by V, here also alpha by V. So this is the concentration at equilibrium stage, 1 minus alpha by V, alpha by V, alpha by V. So here we got three values of number 1 HA, the value of HA, 1 minus alpha by V, the value of H plus alpha by V, and the value of A minus, that will be alpha minus V. Now we are substituting these three values 1, 2, 3 in this equation, which is equation number 1. This equation, which is equation number 1, that we have discussed already. Acid dissociation constant K is equal to concentration of H plus into concentration of A minus divided by concentration of HA. So this is our equation number 1. Now we are putting these three values 1, 2, 3 in this equation. So this equation becomes K is equal to concentration of H plus. Concentration of H plus means alpha by V. Concentration of H plus means alpha by V. Bracket into concentration of A minus. Again alpha by V divided by concentration of HA. We got 1 minus alpha by V. We got 1 minus alpha by V. So in this way we are putting these three values in this equation. By solving this, you will getting, when you solve this, we will getting when you solve this whole term, we will getting K is equal to alpha square one minus alpha square divided by 1 minus alpha by V. Because when you're doing this, V and V get cancelled. V and V, 1 V and 1 V get cancelled. So we have K is equal to alpha square divided by 1 minus alpha into V. Now we know that this V means 1 by V, and we know that 1 by V means concentration C, which is the initial concentration of the acid. We know that the definition of acid, number of moles divided by the volume. So we can 1 by V is equal to concentration, means C, concentration of what? Concentration of weak acid. So we are putting the value of 1 by C, 1 by V is equal to C in this equation. So it becomes Ka is equal to alpha square C divided by 1 minus alpha. Now we are solving this term 1 minus alpha. We know that alpha is very small in case of weak acid, because weak acid only partially dissociated, only small extent dissociated. So alpha is very small. Alpha is very small as compared to the 1. So we can consider 1 minus alpha is equal to 1, because alpha is very small. So we can consider 1 minus alpha is equal to 1, because the value of alpha is very small. So that is why we can consider 1 minus alpha is equal to 1. So this equation becomes Ka is equal to alpha square C. Now we will calculate the value of alpha. So alpha is equal to final equation, alpha is equal to square root of under root of Ka by C. Ka by C. So K is equal to alpha square into C. So here we will calculate the value of alpha from this equation. So alpha is equal to K by alpha square is equal to K by C. So alpha is equal to under root of K by C. So this is our final equation. Alpha is equal to under root of K by C, and which is nothing but the Ostwald dilution law for weak acid. So that was regarding the Ostwald dilution law for weak acid. Ostwald dilution law in case of weak acid such as HA. Now here I am going to start Ostwald dilution law in case of weak base. We already know that Ostwald dilution law is a relation between degree of dissociation alpha and dissociation constant K. Now let's see the Ostwald dilution law in case of weak base. So here I have taken a weak base such as BOH. So I can represent weak base like BOH in aqueous medium. So we know that when weak base such as BOH, when dissolved in water, it dissociates into ions such as B plus plus OH minus. So because weak acid is there, reversible one, which means double headed arrow between reactant and product in case of weak substances such as weak base. So weak base, I have taken a BOH in aqueous medium, which means when BOH dissolve into the water, it dissociate into ions, one positive ion and other is a negative ion, B plus plus OH minus. In the last case, we have seen the Ostwald dilution law in case of weak acid, and that case I have taken a weak acid such as HA, and dissociation of HA to H plus plus A minus. Now here Ostwald dilution law in case of weak base, that is why I have taken a BOH, and when BOH dissolve into the water, aqueous medium, it dissociate into ions, positive ion, negative ion, B plus and OH minus. Now similarly, we will understand what is dissociation constant, base dissociation constant in case of weak base. We know that dissociation constant means K, and here we will find out base dissociation constant means we can use Kb term. So Kb is equal to Kb means base dissociation constant. In the last case, Ka means acid dissociation constant. K for constant, B for base. So Kb combinedly called base dissociation constant. Now Kb in case of weak base is equal to product side, concentration of product side above the line. So Kb is equal to concentration of B plus concentration I am representing with square bracket concentration of B plus into concentration of OH minus. We cannot use the plus sign in case of acid dissociation or base dissociation constant. In case of acid or base dissociation constant, we can use multiplication term, not plus sign. We can use plus sign in case of only dissociation of acid or base, but we cannot use plus sign in the case of Kb or Ka. We can use here multiplication sign. So Kb is equal to concentration of B plus into concentration of OH minus divided by concentration of BOH. Concentration of BOH. So this is our equation number 1. This is our equation number 1. So as I said, the product side means ion side are always above the line, numerator part of the division, and reactant side below the line in case of base dissociation constant or acid dissociation constant. So this is the Kb base dissociation constant for weak base. This is equation number 1. Now I will again write this reaction for weak base, dissociation of weak base. BOH is equal to BOH is equal to BOH dissociate B plus OH minus, B plus OH minus, aqueous medium, aqueous medium, aqueous medium. Now we know that we have again three condition. Number 1, at time t is equal to 0 before the start of the reaction, then t at equilibrium, and amount concentration at equilibrium stage. So before the start of the reaction means the reaction is not start yet, so t is equal to 0, time t is equal to 0 before the start of the reaction, then t amount of the substance at equilibrium, and last condition concentration at equilibrium. So first let us see the t is equal to 0. Suppose we have number of moles is equal to BOH only 1, means we have only 1 mole of BOH at t is equal to 0. Suppose we have only 1 moles of BOH before the start of the reaction. So value of B plus OH minus is equal to 0. Here we are considering only 1 moles of BOH as I said in case of weak acid. In case of weak acid, we consider only 1 mole of HS. Similarly, in case of weak base, we consider only 1 mole of BOH before the start of the reaction. Now, when reaction reaches at equilibrium stage, out of 1, only alpha moles dissociated. So out of 1 at equilibrium stage, only alpha moles dissociated. So how many remaining BOH molecules? What is the value of BOH after removal of alpha? When out of 1 only alpha mole dissociated, means how many moles remaining of BOH? 1 minus alpha. 1 minus alpha. This example that we have already seen in the last part in case of weak acid. Suppose we have 100 moles of BOH, and out of 100, suppose 5 moles dissociated, means 5 B plus and 5 OH minus. So how many moles remaining in case of BOH? 100 minus 5 means 95. Now here I am considering 100 means 1, 5 means alpha, and 100 minus 95 remaining molecule of BOH means 1 minus alpha. So 1 means 100 and alpha means 5, and 1 minus alpha means 100 minus 5. So out of 1 only alpha mole dissociated. So because removal of alpha from 1, the moles remaining of BOH is equal to 1 minus alpha. Now we look at the last term, concentration at equilibrium, and we know that concentration means number of moles divided by the volume. So we can divide each term by volume. So 1 by alpha divided by V, alpha by V, alpha by V. So this is the concentration at equilibrium. Concentration of BOH 1 minus alpha by V, concentration of B plus alpha by V, concentration of OH minus alpha by V. Now we have the three values, BOH, B plus and OH minus. So now we are substituting these three values in the equation number 1 in place of B plus, OH minus and BOH. So this equation becomes KB is equal to KB means what? Base dissociation constant. So KB is equal to concentration of B plus, concentration of B plus, alpha by V into concentration of OH minus, alpha by V divided by concentration of BOH, 1 minus alpha by V, 1 minus alpha by V. So by solving this, you will find that the V will get cancelled. So remaining equation by solving this, KB is equal to by solving this, alpha gets VV gets cancelled. So remaining equation, alpha square divided by 1 minus alpha and remaining 1, we left with 1V. So alpha square divided by 1 minus alpha into V. Then further part, in case of weak base, we know that this term means V is the denominator part, so we are considering 1 into numerator part, and we know that 1 by V is equal to concentration C, initial concentration of the base. So 1 by V is equal to C, 1 by V is equal to C, initial concentration of the base. Now we are putting the value of C in this equation number 2. So this equation becomes KB is equal to alpha square C divided by 1 minus alpha. Now we know that the value of alpha is very small. Alpha is much less than 1. So we can consider 1 minus alpha is equal to 1 because alpha is much less than 1. So alpha can be neglected. So we can considering 1 minus alpha is equal to 1. So this equation becomes KB is equal to alpha square C. Now the last relation, we will calculate the value of alpha. So alpha square is equal to KB divided by C. So what is the value of alpha? Alpha is equal to alpha square is equal to KB by C. So alpha is equal to under root of KB by C. Alpha is equal to under root of KB by C. So this is our last equation which shows the relation between alpha and K, degree of dissociation and degree of dissociation and dissociation constant that you got. Alpha is equal to under root of KB by C, and this is our Ostwald dilution law for weak base. So this is the last equation, major equation, your final equation. Ostwald dilution law for weak base is equal to alpha is equal to under root of KB by C. So